Hello everyone, Tripster here, and today we're doing a Mythbusters video on what's more important for acceleration, high horsepower or high torque. I did a paper on this back in college for my mechanical engineering, and I recently was able to find the Excel spreadsheet that I did for my presentation. So in this comparison, we're going to compare a high horsepower, low torque engine versus a high torque, low horsepower engine. So we're going to keep as much of the car as we can the same. We're going to keep the weight the same. We're going to keep the same wheels. We might need to change the transmission just because a high RPM engine that makes very low torque is going to have a much higher top speed than a low revving high torque engine. So we'll need to adjust a little bit with the final drive, but everything else we're going to keep the same as much as we can. The first part here is horsepower. You just plug those numbers in. The second number here is torque, foot-pounds of torque, and the formula for that is you take the horsepower multiplied by 5252, and then you divide it by the active RPM range. I learned physics in metric, so metric is a little easier for me, so I convert everything from the horsepower and foot-pounds of torque into metric. Kilowatts is the metric equivalent. To convert horsepower into kilowatts, you take the horsepower multiplied by 0.74, and that's what you get for kilowatts. The Newton meter is the torque equivalent, so you take kilowatts multiplied by 9550 and you divide it by the active RPM range. So that's how you convert kilowatts into Newton meters. The portion down here is car weight. Up top is in kilograms. We're going to be using that for the acceleration. Down here is the car weight in pounds. This is not actively used in my calculations, but I included it for it's helpful if you don't know kilos well. The wheel diameter is in centimeters. We're going to be adjusting that a little bit. The wheel diameter here, that's just a number in inches. Again, not actively used. I just included it for more information on the screen. And then the wheel circumference, that's in centimeters. You take the wheel diameter and you just multiply it by pi. So here we go. The circumference of a circle, 2 pi r, 2 times pi times radius, or pi times diameter. So that's what wheel circumference is. The final drive, that's like the differential, and the transmission ratios are here. The next portion here is the kilometers of the speed of the vehicle. So in first gear with 1000 RPM, the vehicle is going to go 10 kilometers an hour using the current final drive and transmission ratios. Second gear, it's going to go 15. Third gear is going to go 20, and so on. To explain the numbers, you take the RPM that we're currently using, multiply it by the wheel circumference, which is in centimeters, and then you divide it by the final drive and the transmission ratio for, in this case, first gear. The next portion here, which is that 60, we're using kilometers an hour. Over here is revolutions per minute. So to convert minutes into hours, we multiply by 60. And the final portion here is this is wheel circumference in centimeters. This is speed in kilometers. So to convert centimeters into kilometers, we just multiply it by that, and that gives us the speed. So that's what the orange cells here represent. So the next field here is where the physics begins. Newton meters at the axles, and again that's for first gear, second gear, third gear, and so on. So let's pull up a paint here. I'm sorry about my drawing. It is not easy to draw with a mouse, but I will do my best. So here we have an engine, and that's the pulley up front. Let's say that's a intake manifold, throttle body here. After that we have a transmission. Then we have the differential, the drive shaft. Then we have the differential, and then we have the axles. Here we go. So that's what the next field represents. So let me change the color here. So we have the engine that's spinning here. The drive shaft is spinning here. Multiplication happens at the transmission. Multiplication happens at the differential. And then from there we have torque at the axles. We have two axles. However, because the total force pushing the vehicle is going to be the same with both wheels, assuming none of them are spinning, we basically, if we want to, we can divide it by 2 because it's 2 tires, but because the total is applied to the ground by both tires, we're going to multiply. So for the calculations, we're just going to eliminate times 2 and then divide it by 2. So the next number here it represents the torque at the 2 axles here. So here and here. So that's what these blue cells represent. So to go over the physics, we take the torque of the active RPM range, and then we multiply it by the final drive and the transmission ratios. It's very simple. Here it is for the first gear, here's this for the second gear, third, and so on. Now down here, that's where the fun begins. We're talking about the power that the vehicle is going to put to the ground. So let me pull up my drawing here. So let's say we have a funny looking car. Okay, so that somewhat looks like a car. We'll put a ground on the bottom, and then we'll put some tires. Okay, so we want the vehicle to go forward, right? Which means the tires are going to spin in this drawing. They're going to spin counter clockwise. The force they're going to apply is backwards, and then the road is going to push forward, right? So that's how the physics works. What we're interested is this number right there. So how much force is the car going to put to the ground to accelerate forward, right? So let's make a bigger wheel so it's a little easier to see. So this portion here is the radius of the wheel, and what we're interested is how much force it can put to the ground, which is right there, right? So let me see if I can find the formula needed to calculate that. Here we go. So how do we calculate torque based on the rotation, right? So torque is force times leverage, basically, radius. So we multiply the force times the radius, so we know what the torque is at the axle. We want to know what the force is, and we also know what the radius of the wheel is. So torque Fr. So again, back to this, we know what the torque here at the center is. We know what the red portion here is, and we're trying to find the force to the ground. Okay, so let's go to the spreadsheet. L2, which is the torque at the axle, which is that number here, and then we divide that by the wheel diameter. However, because we need the radius, that's why we divided by 2. So 65 wheel diameter, we divided by 2 to get the radius. And then this part here is Newton meters, and down here is newtons. So that's why we multiply the bottom portion, the denominator, from Newton meters into newtons. So that's what that portion here represents. And again, the torque that you can apply per gear is going to be different because the ratios are different. So there's the different ones, and again, they change based on RPM of the engine. So the next portion here is the acceleration. That's of the vehicle. Force equals mass times acceleration, right? So force equals MA. In order to convert to get the acceleration, you divide by mass, and this crosses out, and force divided by mass equals acceleration. So let me see if, there we go, that's helpful. So force equals mass times acceleration, and we just did the math, so we can convert for acceleration. So that's what this number here means. We know what the force to the ground is, which is this number here, and we divide by the weight of the vehicle, which is the mass, which is here. And then the final number here is a simple acceleration into G's conversion. So acceleration of meters per second squared divided by 9.8, which is G's acceleration. So that's what this number here is. Cool. So let's go over some numbers. Let's start plugging in some numbers and see what we get. So I pulled up a real car example here. So an S2000, 3 point. Here, I'll actually move that on my second screen so I can plug them in. First gear is 3.13, second gear is 2.05, third gear 1.48, fourth gear 1.16, fifth gear 0.94, and sixth gear is 0.67 ratio, and the final drive is 4.1 for this vehicle, right? The next portion that we need, you can see the ratios all match up. The next portion that we want to plug in is the tires, because I think these tires might be a little big for my example here. Here we go. Rear tire size. Let me pull up a calculator here. Okay, so 245 divided by, and then by radius is 17. Yes, fill numbers only, please. Okay, here we go. So the total diameter for this is, where'd it go? Here it goes. 24.7 inches, right? So we will need to plug in some numbers to get 24.7. I could use a calculator to get out this, but okay, that's close enough. So 24.7 wheel diameter is roughly 62.8 centimeters, which is going to be 197 circumference of this size wheel. The next portion is we need to calculate torque or horsepower. So for the first example, let's do a high torque engine, low horsepower. So we have, here we go, we got another calculator here. So we want to, for the example, we want to get 500 torque. So 500 torque, and we need to calculate how much horsepower and at what RPM. So 3000 RPM maybe. Let's try that. So it's going to be a little low. So let's, okay, perfect, right on. So in order for us to get 500 horsepower engine that has maximum of 300 horsepower, we are going to have a very low revving engine of 3200 RPM. So let's plug in some numbers. So over here we're going to have 300. Here we go. So because of the resolution of this, we're going to have a little extra torque basically, so which is fine. We'll keep it as same as we can, but we're not going to get it perfect. So okay, 250. I'm trying to make it more realistic as I can. That's not going to work at all because and then okay, so that's a little more realistic here. So this engine is going to make 75 horsepower at 1000 RPM, which is roughly 400 torque. 2000 RPM is going to make 175 horsepower, which is 460 torque. At 3000 RPM, it's going to make 300 horsepower, which is 525 foot-pounds of torque. And then at 4000 RPM, it's going to make roughly 328 foot-pounds of torque. So the most important part here is this figure right there, which is 525 foot-pounds of torque and 300 horsepower. So we're giving this engine a little bit more. So, and we will need to adjust the top speed because this engine is going to have 114 kilometers top speed. That's not going to be enough. So let's try maybe 3.9. That's still not going to be enough, but okay, that's more reasonable. So we're going to have about top speed of 200 kilometers. Okay, so let's say that is going to be our top speed of the vehicle, 200 kilometers, which is 120 miles or so. It's very low, but we're trying to get a decent example here. And the torque figures at the axles are going to be as such. So where is our acceleration? Here we go. So in the first gear is very high acceleration just because you have a very high multiplier. So as you get closer to the end figures here, you can see the acceleration just drops off because the higher the top speed, the higher the vehicle speed, and then the gear multiplier is going to be much lower. So let's say in 6th gear for this vehicle, the top acceleration is going to be 3.95 meters per second squared, which is acceleration of 399, so 0.4 just about. So that's our first example. So let me duplicate that, and let's plug in some numbers for horsepower. So that's our torque. The second one is going to be horsepower. So for the second engine, we're going to have a very high revving engine that's very low torque. So let's pull up our calculator again, and we're going to switch it. There we go. So we want 500 horsepower, and we want to see what kind of torque at what RPM this will provide. So maybe 8,000 RPM. That's a little too high. So let's try something a little more. 9,000 RPM. No, it's way too low. So that's the cells that I have. So I guess we'll use that. So for this engine is going to make 500 horsepower at 9,000 RPM, and that's going to make 291 foot-pounds of torque. So that's going to be here, 500 horsepower. And again, that's going to be something like a motorcycle engine or a Formula One engine, something of that sort. So let's plug in some numbers for a reasonable engine that will make Okay, so that's more reasonable, and let's give it a 10,000 RPM red line. So that's going to be 400 maybe. There we go. That's, so you can see that's pretty reasonable graph for a high revving or low torque engine, right? So yep, that's very decent. So the horsepower and foot-pounds of torque are the red ones. So you can see it's very high horsepower, and then the foot-pounds of torque is under 300. So the next issue is you can see the speed of this engine, the speed of this vehicle is going to be 500 kilometers. So we'll need to play with the final drive to get the two vehicles to match up. So we want top speed of 200 kilometers. So a little more. And I think this vehicle was 201, so let's add a little more. Too much. There we go. So that's close enough. So in order for this vehicle to have the same top speed, we need to have a very high drive, final drive. So that's going to be this much. So here's some numbers for you. The acceleration at very low RPM is going to be very low. Let me see if I can pull up the numbers here. Paste values only. Here we go. So the bottom numbers here are for the first vehicle, which is very high torque. The second vehicle here is the very high horsepower. So okay, so we can see that the numbers up here are better for the high torque. However, you're racing, you're not driving around town, right? So in a Formula 1 engine, you're not going to be racing at, 1000 RPM, 2000 RPM. You're going to be racing at the top, 7,000, 8,000, 9,000, 10,000, something like that, right? So when we look at the comparable numbers down here in the race conditions, how do they compare? Well, in first gear at 7,000 RPM, this vehicle is going to accelerate with 13.3, where if we look at the peak, which is 500, which is what we wanted, the highest acceleration at first gear is going to be 22.247 meters per second squared. The highest acceleration of the second vehicle, which has more than 500 foot-pounds of torque, is going to be only 16. If we compare the acceleration in G's, again, that's in first gear, this vehicle, assuming traction doesn't break, right, is going to have 2.2 G's of acceleration, where the high torque engine is going to have only 1.6 G's of acceleration. And the numbers get progressively worse with each gear. So fifth gear, 0.494, and then this one is 0.682. So based on these calculations, horsepower is king for acceleration. And even if you were to look at area under the curve, again, you're not going to be racing at 1,000, 2,000, 3,000 RPM on a Formula 1 engine. You're going to be racing basically these 4,000 or 5,000 RPM range. So you can see the area under the curve is so much higher for the high revving, low torque engine. Anyways, hopefully that concludes it. If you disagree with my calculations, if you found an error somewhere, please let me know in the comments. And if these results surprised you, again, let me know in the comments. Let me know what you think. Like and subscribe, and I will see you in the next one.